I think we're going to do some book learning. All right, well, since we're going to be doing some book learning, I got to put these on. All right, there's a book out there in cyberland, actually in physical land too, that Martin over at Old Foundry Man has been recommending to me and others to read. One of the other guys that he recommended this book to was Walt Sorensen. And Walt found the book online for a pretty good price. He found it for $30 online, and he sent me the link to it, and I went ahead and got it. I didn't realize that it was what a value it is. It's like 3 cents a page. If you figure that out, it tells you it's 1,000 pages long. The thing is huge. I don't know that I'll ever get through the whole thing because I read like 2 words a minute, but this is the book. Can you read that? Is it too bright? I don't know if you can see that. I can't see it. There it is. It's called the Complete Casting Handbook, Metal Casting Processes, Metallurgy, Techniques, and Design by John Campbell. This is the 2nd edition of this book. And this apparently is the definitive answer to metal casting. And I've looked at it, and there is a ton of information in this book. 1,000 pages, you'd expect it, right? But it has more stuff than I could even think of. And it's got a lot of stuff in there that quite frankly, I skimmed through it and I looked at it and I said, man, am I ever going to understand this? We're going to try. So here's what we're going to do. Today I want to introduce you to what's called the 10 rules for good castings. 10 rules for good castings. I'm going to introduce you to them. I'm going to talk a little bit about some of them with the idea of just showing you where I screwed up, didn't follow this stuff. I'm telling you right off the bat, some of them I have no clue what he's talking about. But we're going to introduce it. I'm not going to go into depth. I'm not going to talk about a lot. I'm just going to introduce you to the topics. And then my goal is to maybe do a video per rule just to kind of talk about it, explore it, maybe show you some things that I did that were wrong, some things that I'm doing that I think are right, and move through this book. I think there's some great information in here. I realize a lot of you guys are not going to go out and buy the book and read through it, but maybe I can give you some stuff out of here that will help and will kind of guide you on the right path, right? And there's clearly some things in here that are not approved. Approved is probably the wrong word, but you look online and you watch some of these castings, and they definitely didn't come out of this thing. So let's go ahead and get started. All right, rule 1. Start with a good quality melt. Immediately before casting, the melt should be prepared, checked, and treated if necessary to bring it into conformance with an acceptable minimum standard. Prepared and used so far as possible only near defect-free metal. I fail because, like a lot of you guys, this is what my my source material looks like. It could be cans. It might be stuff that I've melted in the past. It might be extrusion. Heck, I've even got aluminum horseshoes over there that I haven't melted those in a while, but yeah, I fail. Martin is on me continually, well, not continually, but he's on me a lot to use certified ingots, so you know what it's going to do when you melt it. You know what it's going to do when you pour it and cast it. I don't do that, and maybe I will get there. I keep thinking I'm going to probably get there. I know I'm not adverse. I'm not adverse to doing the right thing, but that's the first one. Rule number 1. All right, rule number 2. Avoid turbulent entrainment of the surface film on the liquid. This is a requirement that the liquid metal front, the meniscus, should not go too fast. Maximum meniscus velocity is approximately 0.5 meters per second for most liquid metals. 0.5 meters per second. I'm going to talk about that here. This requirement also implies that the liquid metal must not be allowed to fall more than the critical height corresponding to the height of a sessile, S-E-S-S-I-L-E, drop of liquid metal. The maximum velocity may be raised to 1 meter per second or even higher, and the critical fall height might be correspondingly raised to 50 millimeters in sufficiently constrained running systems or thin section castings. All right, I come close. Here's the deal. My flask, let me just point it over here real quick. All right, this is my cope. It's upside down right now. I just emptied it out. But it is right at 80 millimeters. You may not be able to see that, but it really is it says 8 right there. 80 millimeters high. That's how tall my cope is. And as a result, my sprue height is about 80 millimeters. Not, what do you say here, 50 millimeters? But that's okay. Here, let me tell you why it's okay. First of all, when you calculate, and I'm going to get into, when we get into this rule number 2, I'm going to get into more detail. If my metal was free falling at that height, at 80 millimeters height, at 80 millimeters, the metal would achieve 1.2 meters per second. Well, that is twice, almost 3 times the speed that he recommends at half a meter a second. But we have to consider too, I'm inside a pipe, and that will affect the speed at which things flow. It's a constrained pipe. One of the things that we'll talk about later on is how the metal on the outside flows slower than the metal on the inside. So we're actually probably we're not doing free fall speed, we're doing a little bit slower than that. I'm probably sub-meter. I'm hoping I'm sub-meter per second by the time I hit the bottom of my sprue. But something to keep in mind, you see tall sprues, you see wide open sprues, right? And metal coming down. That metal is coming down really, really fast, especially when you consider the pour height. When you pour it out of the flask, and there's a gap, and then it hits that tube, which is unrestrained, it comes down. You could be way, way, way up there, and 2 or 3 or 4 meters per second at that point, because it's accelerating as it goes down. So that's a big deal. That's something that I try to do, and I think this is one of the ones I do right. But we'll talk about this when I get into rule number 2. All right, rule number 3. Avoid laminar entrainment of the surface film on liquid. This is the requirement that no part of the liquid metal front should come to a stop before complete filling of the mold cavity. The advancing metal meniscus must be kept alive, and he's got alive in quotes, i.e. moving, and therefore free from thickened surface film that may be incorporated into the casting. This is achieved by the liquid front being designed to expand continuously. In practice, this means progress only uphill and a continuous, uninterrupted upward advance, i.e. in the case of gravity-poured castings from the base of the sprue onwards. This implies only bottom gating is permissible. No falling or sliding downhill of liquid metal is allowed. No horizontal flow of significant extent. No stopping of the advance of the front due to the arrest of pouring or waterfall effects, etc. Let me show you this. Get this. Okay, this is a bronze casting that I did, and this is my my pour. I had the basin, I had the sprue. I talk about this all the time, right? Sprue comes down, and I've got it coming into a runner across the bottom. You see how it comes across there. Now, so what's going to happen is this metal is coming down, and it's going to run over to here. It's going to stop. Now, it is going to continue to move. It's going to keep moving upward. This is only going to stop for a fraction of a second, but it's going to come this direction, stop, and then start to fill up. once it fills up, it's going to fill up into this feeder, this gate-ish kind of thing. It's more like a gate. I guess it's more of a feeder, or maybe it's another runner. I'm not sure what exactly you would call this thing. But it comes up into that, and then it flows out from there, and it will flow out into these gates that I've built onto here. Now, this was actually a failure that I'll talk about when we get into, actually I'm going to probably save this for one of the feeding rules that will come much later. But this one didn't work. But anyway, this is how it works. And then the metal flows into my part, and in this case I have a vent on the backside so it can come up the vent. Now, is that right or wrong? I don't know. I feel like I've had pretty good success with this method. I feel like I've kept the metal flowing. It never stops directly because it comes in and starts coming up and then goes out. And I don't know that I don't know. This is something that we're gonna have to figure out. But I think this is okay, but I don't really know. So that's rule number 3: avoid laminar entrainment. All right, rule number 4: avoid bubble entrainment. All right, so entrainment, I didn't mention it. Entrainment means to incorporate. If you don't know, I had to look it up. That's what I'm telling you. No bubbles of air entrained by the filling system should pass through the liquid metal in the mold cavity. This may be achieved by properly designed offset step pouring basin. I think that's what I'm doing, is a offset step pouring basin. Fast backfill of properly designed sprue. I think that my ridge gives me a fast fill of that thing because I keep the metal stays up above the ridge, so it's constantly keeping the sprue full. Preferred use of stopper. I don't know what a stopper is. Avoidance of the use of wells and all other volume increasing features of filling systems. There's no well down there. You notice that a lot of times you'll see a sprue come down, a big fat sprue come down, and there'd be a big well down here. And I started off doing that. That's because it just felt right. He's saying don't do that. Let's see. Small volume runner and or use of ceramic filter close to sprue. Well, my runners are pretty small, I think. Maybe not. Maybe they're big. I hope they're not huge, but I want to make sure I get enough metal in there. So maybe we'll learn something when we go through this chapter about how big a runner really should be. Let's see. Possible use of bubble traps. Again, I don't know what a bubble trap is, unless maybe this is a bubble trap. Maybe I don't know. Naturally pressurized filling system fulfills most of these criteria. No interruptions in pouring. Okay, so that's a biggie. And that one got drilled into my head early on too. When I'm filling this thing, I make sure that my fill, this part never goes empty. I don't see the metal drop down and I've got to fill it over again. I've done that a couple of times, and what ends up happening, in fact, what happened one time to me is, as it was filling and I let it come down, this part cooled and it started choking the top of my sprue because it started freezing. It doesn't take very long, and I didn't have a good pour because I was pouring and I didn't pour fast enough, and then it just drained, and then I tried to increase it. And what that does is that also introduces the opportunity for bubbles, for air to get in there, because you've got a void, and now you're splashing more metal down into it. So try to keep your pours running all the time and keep that bridge full. All right, number 5, rule 5, avoid core blows. No bubbles from the outgassing cores or molds should pass through the liquid metal into the mold cavity. Cores to be demonstrated to be of sufficient low gas content and or adequately vented to prevent bubbles from core blows. No use of impermeable clay-based core or mold repair based. All right, here's the deal on that. Boy, I have struggled with cores, and let me just show you one right here. Okay, so you won't recognize this. You might recognize this. This is a socket that I cast for my brother. He's been looking for me to make him cast him an aluminum socket to try to start a lawnmower. I routinely say I think this is a death wish on his part, but I'm going to make it because it's a cool challenge. Now I made this thing, and it had a core, and I actually have a video on how I made the core mold for this. And the large end I had vented. I had a hole. Actually drilled a hole through it, and it was able to. The gas was able to escape from this end. Now the small side, this side, I wasn't able to do that. In fact, what happened is, and I'm gonna. Here's a spoiler right there, right? At this joint right here, where they transitions from large to small, my core broke, and it wouldn't hold together. So what I ended up doing was putting it back together and pouring more of my sodium silicate material on there. And I had a system that had way too much sodium silicate in it right at this, for this piece here. It was almost like just a hard block of it. Well, when I poured this thing, and I didn't vent it because I couldn't get a hole, it's so tiny, and it was so fragile, drilling a hole through it was just a recipe. I figured there's no way. Well, here's what happened when I poured it. You can see the gas that happened. You can see how this this bubble, if I bring it up, does that help? Yeah. See the shape? I mean, that's all, I believe that is all due to gas that came out of that core. It didn't have anywhere else to go, so it formed a bubble around this thing. That stuff actually foams up. If you have too much of it and you heat it, it'll actually, you'll see it just kind of like foam up. That's what he's talking about. Don't do that. All right, rule number 6, avoid shrinkage. No feeding uphill in larger section thickness castings. No feeding uphill in larger section thickness castings. Feeding against gravity is unreliable because of 1, adverse pressure gradient, and 2, complications introduced by convection. Demonstrate good feeding design by following all 7 feeding rules, which we're going to talk about in another set. I looked at those. There's some stuff there that I need to learn. Feeding rules by an approved computer solidification model and by test castings. Well, I do lots of test castings. I call those failures a lot of times. I don't have any computer simulation. Once good feeding is attained, fix the temperature regime by controlling the level of flash at mold and core joints. Mold thickness, mold coat thickness, if any, and temperatures of metal and mold. Okay, so my molds, one thing I'm learning about molds, my Petrobond, my oil, I don't know if it's called Petrobond anymore, it's oil-based sand at this point. When it gets warm, it doesn't hold together. It loses all of its stability, and I think it's because the oil loses its viscosity. When it's thicker, when it's cold, it's thicker, it's stickier, and it holds the sand together. I was out here trying to cast something the other day. It was over 100 degrees in here, and the mold, I picked it up and it just collapsed on me. And because the sand was warm. I mean, it was warm to the touch. So I'm not sure that this applies to oil-based sand, this warm, keeping your molds warm. I see a lot of guys with green sand, the water-based, that bake their molds and stuff. That is clearly a technique that gets used. I just don't think you can do it with sand, with oil. And I also don't understand what he's talking about don't feed uphill, because earlier he talked about feeding uphill. So we're gonna have to figure that out. That's avoid shrinkage. Oh, and and the feeding thing. Let me get into that too. I'm gonna touch on it. The feeding stuff talks about whether or not you should put feeders on or not. And he kind of recommends, as a general rule, try not to use feeders. Well, I can tell you for a fact that some of the things that I cast, like the hammerhead, if you ever watch my hammerhead video, and it's a metal like this bronze, which wants to just shrink like a frightened turtle. It's got to have feeders. It's got to have a source of metal to go in as that's cooling. The aluminum stuff, the thin stuff I'm doing, yeah, there's no feeder necessary on that. Even on the bronze stuff, there's really no. This thing that I cast, This is the kind of the finished thickness of the part, this little piece right here. And it doesn't need a feeder. Okay, rule number 7. I told you I didn't understand some of these things. This is one of them. Avoid convection. Assess the freezing time in relation to the time for convection to cause damage. Thin and thick section castings automatically avoid convection problems. Thin and thick section castings. So if it's thin, it avoids it. If it's thick, it avoids it. We're going to have to read about that. For intermediate sections, either 1, reduce the problem by avoiding convection loops in the geometry of the casting and rigging. Rigging, is that what you call it when you make all the gates and stuff? Rigging? Avoid feeding uphill. Well, there it is again. Avoid feeding uphill. Or 3, eliminate convection by rollover after filling. I don't know that. I'm telling you right now, I don't understand that. All right, rule number 8. Predict segregation to be within limits of the specification or agree out of specification compositional regions with the customer. Avoid channel segregation formation if possible. I thought we did away with segregation back in the 50s. I don't understand that one either. Another one to learn. Nine, reduce residual stress. Oh, this is a biggie for me. No quenching into water, cold or hot, following solution treatment of light alloys. Polymer quenchant or forced air quench may be acceptable if casting stress can be showed to be acceptable. All right, so here's the deal. So from my blacksmithing time, the experience I got there, I know that when you quench metal, it changes the characteristics of that metal, or it locks them into a certain state. Because when you anneal metal, you tend to relax it, kind of soften it up. When you quench it, a lot of times, what happens is you are hardening it. With some steels, especially, that quenching, you'll get it to a critical temperature. You'll quench it in oil or quench it in water, cool it very rapidly, and it will it stays in a more crystalline structure or something. I could be wrong, but it stays in a state that allows for a very hard but brittle edge. A lot of times you'll see that with knife forging, knife making. They'll quench them, they'll get a very hard edge so it stays sharp, but if you were to hit it on something or you pry it on something, it'll just snap like it's glass. I know quenching affects it, and I see guys quenching their castings and their ingots all the time. And I've quenched my ingots because I figure, well, I'm going to melt them again, and that's going to take them out of whatever state they're in and put them in a fluid state again. But this idea of quenching my parts has bothered me. I've done it because I'm in a hurry and I want to get it cooled off so I can touch it and look at it. But I'm not sure that it's the best thing to do for the metal. So I'm looking forward to that chapter. All right, last rule, rule number 10. All castings to be provided with location points for pickup for dimensional checking and machining. Proposals are to be agreed upon with quality author, machinist, etc. Well, okay, so that's not going to apply to me. I don't think, unless I got into like doing this for a living and I was making parts for people and they had to measure them and assure that they were the right size and everything. But that's, I think, is basically going to talk about provide points on the casting where you can actually pick it up without damaging it, that you can measure it so you understand that if this section is this big, the rest of it should be, within tolerance as well. So I think that's what we're going to get into. I don't know that that's going to apply to me, but we'll see. Anyway, so there we go. There are the 10, what do you call them? 10 rules for good casting is in chapter 10. If you get the book, I'll put the link down below in the description. Thank you, Walt, for pointing it out. Thank you, Martin, for harping on me. I got an email from Martin this morning. He said, and I told him I was going to do this video, and he told me, he said, well, now that you've got this information, I expect to see a lot more improvement in your castings. Martin, I hope I don't disappoint. I'm trying, but I know that there are some things like rule number 1. I just won't show you what I melt. I won't show you what the ingot started as, and you'll believe that it's okay. Anyway, there you go. 10 rules for good castings. I think we're going to try to do a video on each chapter and just get into it a little bit more as I read and as I understand, and I am able to maybe impart that information back. I'll do videos. I don't want to get into them too deep now because, quite frankly, you've read now what I've read. So there we go. That's it. I want to tell you guys to, you know what? You have a great day.